Welcome to another video for Stat 420. In this video, we're going to talk about the standard deviation and standard error for our simple linear regression estimates. So specifically talking about how do we measure variability for measures like beta, beta hat naught, and beta hat 1. So first, I'm going to move my picture first. Second, I'm going to talk about what a standard deviation is and how we've typically kind of seen it before and would think about it. Right, so standard deviation is a measurement of variability in a particular variable. So typically we think about the standard deviation of one variable, we'll just call it x, and if we were to calculate the square deviations of each data value from the mean of that distribution, sum them up and divide by n, I'd get kind of this average deviation from the mean. So it's a little bit different. You know, when we say it's kind of like the average deviation, I guess if I really wanted to find the average deviation, I would sum all the absolute value differences up and divide by n. But there's reasons in statistics why we use this convention that we're not going to get into. But the bottom line that we're trying to get to here is that this is a standard deviation. It's measuring variation in a particular variable. It's measuring basically average deviation from the mean. We can measure this as a parameter if we had all of the data values in a particular population we're looking at, or we could calculate a sample standard deviation if we're looking at only a sample of data from a particular population. So a sample statistic is going to be estimating the parameter. The parameter is a constant, it is a singular value. A sample statistic is going to depend on the sample and it's going to be different for each sample that we might take from the population. So likewise, we can also calculate a standard deviation of a sample statistic. So what we mean by that is when we're looking at a sample statistic like beta hat naught or beta hat 1, we recognize that there's a distribution of possible values that I could get for each of those sample statistics, right? So if you think about it, if I am randomly sampling from a particular bivariate distribution, then with each bivariate sample I take, I'm going to get some value for, say, beta hat naught, and it's going to follow this distribution that's centered around the true parameter, beta naught. Sometimes my beta hat naught will be below it, sometimes it will be above it, but I know that's going to be somewhere in this distribution, and that every time I take a sample, I'm going to get a slightly different value. So this is the distribution of possible beta hat naught statistics. So because of that, there is a standard deviation for beta hat naught. If we think about beta hat naught kind of like a random variable that it can take any of these different values, right? So like these are all the different values it can take, some values being a little bit more likely than others. I can represent the variability in beta hat naught as a random variable. And so there exists a true standard deviation for beta hat naught. If I knew the full distribution of beta hat naught, I could calculate the standard deviation for beta hat naught. I could even use the same formula over here. I could plug in the sum of each of my beta hat naughts, but by the ith, each term. So if I have, well, there would actually be infinite in this situation. There's an infinite number of bivariate samples I could take from a population, or something like that. And then I'm comparing that to the actual beta naught value. I could make this calculation. Well, infinity in the denominator doesn't make any sense, but this is some very large number. I'll just call it n because I realize that's going to be very confusing if I'm putting an infinity in the denominator. So from 1 to n, I could calculate the standard deviation of beta hat naught. I could also use this expression here. So this is another way to represent that same calculation, and that is going to be the standard deviation of my residuals times the square root expression. And again, these two measures are representing parameters. They're representing these true standard deviations of these random variables if I were to have all the information, if I knew the bivariate distribution and knew the distribution of each sample statistic as a result. Quick aside, in this class and in the book, we're calling these standard deviations. However, you might come across textbooks or instructors that might also call these standard errors. In fact, I typically do that in Stat 212. I just define a standard error as the standard deviation of any sample statistic, whether it's a parameter or not. Here we're going to be a little bit more picky with our language, and we're going to call this a standard deviation still, and we're going to reserve the term standard error for when we're making this calculation with a sample statistic and making an estimate for it. So the standard error of a sample statistic is going to be when we're trying to calculate the standard deviation, but we're having to estimate it. We're having to use S sub e instead of sigma sub e, right? So it means that these are not going to be parameters. These are going to be statistics that we hope are good estimates of these parameters over here. And I think that's it for this slide. So that means that beta hat naught and beta hat 1, I think that's a weird typo there. This should say the distribution, or honestly, it could just say beta hat naught and beta hat 1 each follow a normal distribution. So beta hat naught and beta hat 1 should each be centered around beta naught and beta 1 as statistics. They should be centered around the parameters they're trying to estimate. And then we can represent the variance of each as just a squared version of these parameters that we saw earlier. So beta hat naught, beta hat 1 are like random variables. They're normally distributed. They have a mean around the parameters they estimate. They have a variance of this term right here. That means that we could also convert beta hat naught and beta hat 1s to a standard normal distribution as well. So if we subtract out the parameters they're estimating, divide by the standard deviation of each of these random variables, then that should approximately follow a normal 0, 1 distribution, a standard normal distribution. However, just like we've seen before, we do need a t-correction in real life when we're trying to estimate this variability, when we're working with the standard error of beta hat naught and beta hat 1 instead of the standard deviation. So these are parameters, but in real life, we're not going to be able to know them because if we're doing inference, like we pretty much always are going to be doing, we're estimating that variability as well. So we're estimating not only these values, but we're estimating the variability of those values. So as a result, these statistics are going to follow a t-distribution. So even though beta hat naught and beta hat 1 themselves are following a normal distribution, when I convert them to standardized scores with these estimates in the denominator, that new standardized score is now going to follow a t-distribution. So the difference here is that a t-distribution has fatter tails, meaning that there's a little bit more variability in the test statistics that I'm going to get here. So because of this estimate, because these are going to have a little bit of variability in themselves, I'm going to see a little bit more variability in the standardized scores that I could get. And that additional variability is going to depend on my degrees of freedom, which in this case is going to be directly related to the sample size that I'm sampling from. So what we're trying to get at here is if I have a really small sample, these estimates are going to have a little bit more error in them, and I'm going to have a little bit more variability in the standardized scores that I produce. If I have really large samples, then these should be pretty good estimates of variability, and the error correction I need is going to get smaller and smaller. So the larger your degrees of freedom get, the more the t-distribution does begin to kind of converge to the standard normal distribution. And eventually at a point, like usually once we get past like 200 or 300, the distinction is pretty trivial at that point. But as long as our sample is not particularly huge, we should probably be careful and use a t-distribution and include kind of that error correction, that adjustment to that distribution.